Welcome to this biochemistry lecture on carbohydrate catabolism. This is probably one of the shorter lectures just because carbohydrates are the main entry point of glycolysis, and there's not really that overly much amount about entering in there, except for we need to break down complex carbohydrates into monosaccharides. So we'll talk about that and how that allows the monosaccharides to enter into glycolysis. So glycogen is a complex polymer of glucose. Glycogen usually has an alpha-1,4 glycosidic bond, but it also has an alpha-1,6. So it has branching points, and branching points is where glucose, that's where we have enzymes that cleave those specific bonds. So we have enzymes that break the alpha-1,4, and we have enzymes that break the alpha-1,6. Glucose is stored as glycogen predominantly in the liver and muscle cells, and when we get into situations where we're low on glucose, glycogen is broken down into glucose. So the glycogen phosphorylase is the main enzyme that catalyzes the phosphorylated cleavage of the alpha-1,4 glycosidic bond, and it releases glucose 1-phosphate as a reaction. You probably recognized pyroxidol phosphate, or PLP. That's a cofactor involved in that enzymatic process. Here's a picture. There are regulators of this process, including there's some new drugs that exist. Glycogen phosphorylase is a homodimeric enzyme. It is allosterically controlled, as there is a relaxed state, which is the active form, and a tense, which is the inhibited form. You can see the inhibition sites. One of them is a glucose analog N-acetylglucosamine, glucnac, and it's adjacent to pyridoxal phosphate at the axis, PLP at the active site in the crystal structure. There's a new class of drugs developed for treating hypoglycemia. It's a chloroindol carboxamide, which inhibits liver phosphorylase allosterically, and they bind at the dimer interfacing, and it stabilizes the tense conformation. So there's all kinds of ways, and glucnac, or N-acetylglucosamine, is one of those things that people take as a way to restore joints. Probably just an anti-inflammatory, and it probably is as we know, it's an inhibitor of this protein, so probably get less inflammation. So there's also branching enzymes that exist. So again, glycogen phosphorylase breaks down 1,4. There's an amylo alpha-1,6 glucosidase that breaks down the branched form of this enzyme. So there's those are the two enzymes that exist. If you have, and then from there they can follow normal function of the enzyme. Phosphoglucomutase catalyzes the reversal reaction of glucose 1-phosphate, which is what's cleaved off, to glucose 6-phosphate, and there's a serine at the active site that donates and accepts the phosphate group, and then the bisphosphate is not released, and from there this can be processed and transferred to the cell. So we're going to briefly mention here how to manufacture glucagon. We'll talk about biosynthesis in the next chapter for the other biopolymers for glucose, in particular glycogen. We're going to talk about it here. So glycogen synthase makes it by combining glucose 1-phosphate with UTP, and then it becomes UGP glucose, and that's the immediate precursor for glycogen synthesis. Glucose residues are added to glycogen, and UDP glucose is the substrate, and UDP is released as the reaction product. So nucleotide diphosphate sugars are definitely the precursors for the synthesis of these complex carbohydrate chains as well. And UDP glucose is formed from glucose 1-phosphate again. So what happens if we have storage diseases of glycogen? So if you don't have a glucose 6-phosphate, which is von Gerke's disease, you end up with hypoglycemia, low blood sugar when fasting, and liver enlargement. There's all kinds of glycogen storage disease. Type 4 deficiency is a branching enzyme, which is Anderson's disease. You get liver dysfunction. Type 5 is deficiency in the glycogen phosphorylase, which is McArdle's disease, and you get muscle cramps with exercise. Type 7 is muscle deficiency of phosphofructose kinase. You have the inability to exercise. These are just some of the diseases. Glycogen storage deficiency is a big deal. It's it's one of those things that is not optimal, obviously. So other monosaccharides can enter the glycolytic pathway. Hexoses, other than glucose, can undergo glycolysis after they get converted to a phosphorylated derivative. D-fructose, which is present in free-form many fruits and in high fructose corn syrup, and formed by hydrolysis of sucrose in the small intestine, can be phosphorylated by hexokinase, and from there go to fructose 6-phosphate in muscles and kidneys. And this is a major pathway. In the liver, fructokinase catalyzes phosphorylation of fructose, but not as a C6, but as a C1. So that's a little bit different. And then it's cleaved to form glyceraldehyde and dihydroxyacetone phosphate by fructose 1-phosphate aldolase. So there's different mechanisms by which these glucoses these different sugars can get in, but almost all sugars can get into the pathway, into glycolysis. Glycolysis can be regulated, and this is just a reference point for you. I would know this chart for the exam. Thank you for listening, and I look forward to seeing you guys in the next lectures.